It is generally recommended to have an isolated grounding system for production wire welding equipment for several reasons. Firstly, safety is improved. Isolating the welding system from the main electrical grounding system helps prevent ground fault or electrical shocks. In case of a fault in the welding system, the isolated grounding system prevents the fault current from flowing back into the main electrical system. Secondly, performance is enhanced. Isolated grounding systems provide a better welding circuit by reducing interference from other electrical sources. This results in improved arc stability, reduced spatter, and better weld quality. Thirdly, compliance is often required. In some countries, such as the United States, the National Electrical Code, or NEC, requires isolated grounding systems for welding equipment. Compliance with the NEC ensures the safety and proper operation of the welding equipment. To implement an isolated grounding system, firstly, install a separate grounding rod or plate away from the main electrical system grounding. Secondly, connect the welding equipment frame and all exposed metal parts to the isolated grounding system. Thirdly, do not connect the isolated grounding system to the main electrical system grounding. Additional considerations include using a properly sized grounding rod or plate to ensure adequate grounding. Also, regularly inspect the isolated grounding system to ensure its integrity. Train welding personnel on the importance of maintaining the isolated grounding system. The purpose of grounding, in general, is to provide a low impedance path for fault current to return to the source, allowing overcurrent protective devices to quickly clear the faults. This minimizes the duration of a fault, reducing the risk of electrical shock and equipment damage. In a typical electrical system, the grounding electrode conductor connects the neutral point of the transformer or generator to a grounding electrode, such as a ground rod or water pipe. This establishes a common reference point for the electrical system and helps to stabilize voltage levels. Equipment grounding conductors connect the non-current carrying metal parts of electrical equipment to the grounding system, providing a path for fault current to flow back to the source. When a fault occurs, the fault current flows through the equipment grounding conductor back to the source, causing the overcurrent protective device to trip and to energize the circuit. Isolated grounding systems are designed to minimize electrical noise and interference by providing a separate grounding path for sensitive equipment. In an isolated grounding system, the equipment grounding conductor is isolated from the normal built-in grounding system, preventing noise currents from circulating through the equipment. The isolated grounding conductor is typically connected to a separate grounding electrode or a dedicated grounding bus. This helps to reduce the amount of electrical noise and interference that can affect the performance of sensitive equipment. The NEC provides specific requirements for isolated grounding systems in Article 250.146. This section specifies the conditions under which isolated grounding is permitted and the requirements for the installation of isolated grounding conductors. It's important to consult the NEC and local codes to ensure that the isolated grounding system is installed correctly and meets all applicable requirements. When installing an isolated grounding system, it's important to use high-quality grounding conductors and connectors to ensure a reliable connection. The grounding conductor should be sized according to the NEC Table 250.122, based on the rating of the overcurrent protective device in the circuit. The grounding conductor should also be installed in a manner that minimizes inductance and impedance, such as by using a short, direct path to the grounding electrode. It's also important to properly bond all metal parts of the equipment to the grounding system to ensure that there are no potential differences between them. This can be achieved by using bonding jumpers or by connecting the metal parts to a common grounding point. Regular inspection and testing of the grounding system are essential to ensure that it is functioning properly. Grounding impedance testing can be used to measure the impedance of the grounding system and identify any potential problems. Visual inspections can also be used to check for loose connections, corrosion, or other damage to the grounding conductors and connectors. Proper grounding is a critical aspect of electrical safety and equipment protection. By following the NEC requirements and best practices for grounding, you can help to ensure that your electrical system is safe, reliable, and free from electrical noise and interference. The specific requirements for grounding welding equipment can be found in NEC Article 630.11. This section provides detailed information on the grounding of welding power sources, welding machines, and other welding equipment. It's important to consult this section of the NEC to ensure that your welding equipment is properly grounded. In addition to the NEC requirements, there may also be local codes or regulations that apply to the grounding of welding equipment. It's important to check with your local electrical inspector to determine if there are any additional requirements that you need to comply with. When grounding welding equipment, it's important to use the correct type and size of grounding conductors. The grounding conductor should be sized according to NEC Table 630.11, based on the rated primary current of the welding power source. The grounding conductor should also be made of copper or other approved material and should be protected from physical damage. It's also important to ensure that the grounding connection is clean and tight to provide a low impedance path for fault current. The grounding connection should be made to a suitable grounding electrode, such as a ground rod or a metal water pipe. In some cases, it may be necessary to install a separate grounding electrode for the welding equipment to ensure adequate grounding. Regular inspection and testing of the welding equipment grounding system are essential to ensure that it is functioning properly. The grounding connection should be checked for tightness and corrosion, and the grounding conductor should be inspected for damage. Grounding impedance testing can also be used to measure the impedance of the grounding system and identify any potential problems. Proper grounding of welding equipment is essential for the safety of welding personnel and the protection of equipment. By following the NEC requirements and best practices for grounding, you can help to ensure that your welding operation is safe and reliable. The isolated grounding conductor must be green or green with one or more yellow stripes and shall not be smaller than 12 American wire gauge. This conductor is run with the circuit conductors from the power source to the welding equipment. At the welding equipment, the isolated grounding conductor is connected to the equipment grounding terminal. This terminal should be clearly identified and used only for the isolated grounding conductor. The isolated grounding conductor must be insulated along its entire length. This insulation helps to prevent the isolated grounding conductor from coming into contact with other metal objects which could create a ground loop. The isolated grounding conductor should be installed in a separate conduit or raceway from the other circuit conductors. This helps to minimize the amount of electrical noise and interference that can be coupled into the isolated grounding conductor. The isolated grounding conductor should be connected to a dedicated grounding electrode. This grounding electrode should be located as close as possible to the welding equipment. The grounding electrode should be a ground rod, a ground plate, or other approved grounding electrode. The isolated grounding conductor should be tested regularly to ensure that it is functioning properly. The test should be performed using a ground impedance tester. The ground impedance tester will measure the impedance of the isolated grounding conductor. The impedance should be low, typically less than 1 ohm. If the impedance is high, it indicates that there is a problem with the isolated grounding conductor. The problem may be a loose connection, corrosion, or damage to the conductor. The isolated grounding system should be inspected regularly to ensure that it is in good condition. The inspection should include checking the grounding connections for tightness and corrosion and inspecting the grounding conductor for damage. If any problems are found, they should be corrected immediately. The isolated grounding system is an important safety feature for welding equipment. By following the above recommendations, you can help to ensure that your welding equipment is properly grounded and that your welding personnel are safe. In addition to the safety benefits, an isolated grounding system can also improve the performance of welding equipment. By reducing electrical noise and interference, an isolated grounding system can help to improve arc stability, reduce spatter, and improve weld quality. If you are using sensitive electronic equipment in your welding operation, an isolated grounding system is especially important. Sensitive electronic equipment can be easily damaged by electrical noise and interference. An isolated grounding system can help to protect this equipment from damage. When installing an isolated grounding system, it is important to consult with a qualified electrician. A qualified electrician will be able to help you select the right grounding system for your needs and ensure that it is installed properly. The cost of installing an isolated grounding system will vary depending on the size and complexity of the system. However, the cost is typically relatively small compared to the cost of the welding equipment and the potential cost of electrical accidents. An isolated grounding system is a worthwhile investment for any welding operation. It can help to improve safety, performance, and equipment protection. The NEC does not specifically define the term isolated grounding system for welding equipment. However, the NEC does require that welding equipment be grounded in accordance with Article 630.11. This section of the NEC provides detailed requirements for the grounding of welding power sources, welding machines, and other welding equipment. The NEC requires that welding equipment be grounded to a suitable grounding electrode. The grounding electrode must be connected to the welding equipment frame and all exposed metal parts. The grounding electrode must be sized according to NEC Table 250.122. The NEC also requires that the grounding conductor be insulated. The insulation helps to prevent the grounding conductor from coming into contact with other metal objects which could create a ground loop. The NEC recommends that the grounding conductor be installed in a separate conduit or raceway from the other circuit conductors. This helps to minimize the amount of electrical noise and interference that can be coupled into the grounding conductor. The NEC requires that the grounding conductor be tested regularly to ensure that it is functioning properly. The test should be performed using a ground impedance tester. The ground impedance tester will measure the impedance of the grounding conductor. The impedance should be low, typically less than 1 ohm. If the impedance is high, it indicates that there is a problem with the grounding conductor. The problem may be a loose connection, corrosion, or damage to the conductor. The NEC requires that the grounding system be inspected regularly to ensure that it is in good condition. The inspection should include checking the grounding connections for tightness and corrosion and inspecting the grounding conductor for damage. If any problems are found, they should be corrected immediately. The NEC provides specific guidelines on conductor sizing. Grounding electrode conductors are sized according to NEC Table 250.66. This table is based on the size of the ungrounded conductors or the equivalent area for parallel conductors. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Equipment grounding conductors are sized according to NEC Table 250.122. This table is based on the rating of the overcurrent protective device protecting the circuit. The equipment grounding conductor must be large enough to safely carry the fault current back to the source. Bonding jumpers are used to connect metal parts together to create a low impedance path for fault current. Bonding jumpers are sized according to NEC Section 250.102. The size of the bonding jumper is based on the size of the circuit conductors. The bonding jumper must be large enough to safely carry the fault current. According to the NEC, a grounding electrode conductor is used to connect the system grounded conductor neutral or the equipment to a grounding electrode. A grounding electrode is a conducting object through which a direct connection to the earth is established. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductors or equivalent for parallel conductors. An equipment grounding conductor connects the non-current carrying metal parts of equipment, raceways, and other enclosures to the system grounding electrode. It provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. The size of the equipment grounding conductor is determined by NEC Table 250.122, based on the rating of the overcurrent protective device protecting the circuit. A bonding jumper is a reliable conductor used to ensure the electrical conductivity between metal parts required to be electrically connected. This connection creates a low impedance path for fault current, which is crucial for the effective operation of overcurrent protective devices. Bonding jumpers are used to connect metallic parts of equipment, raceways, and other enclosures to ensure electrical continuity and a low impedance path for fault current. The size of the bonding jumper is determined by NEC section 250.102, based on the size of the circuit conductors. Grounding rods must meet certain requirements, including being at least 8 feet long and having a minimum diameter depending on the material. They should be driven into the earth to a depth of at least 8 feet. The location should be free from damage and away from overhead obstructions. Metal water pipes, if used as grounding electrodes, must have continuous electrical connection to the earth and be supplemented by an additional electrode. The water pipe must be in direct contact with the earth for at least 10 feet. Structural metal frames of buildings, if effectively grounded, can be used as grounding electrodes. The metal frame must be electrically connected to the earth. Concrete encased electrodes, also known as U for grounds, consist of at least 20 feet of bare copper conductor encased in concrete. The concrete must be in direct contact with the earth. Grounding plates must have a surface area of at least 2 square feet and be made of metal that is resistant to corrosion. The plate should be buried in the earth to a depth of at least 30 inches. Before starting any work on an electrical system, it is essential to de-energize the circuit and verify that it is de-energized using a properly rated voltage tester. Lockout/tagout procedures should be followed to prevent accidental re-energization of the circuit. Use properly insulated tools and equipment to prevent electrical shock. Wear appropriate personal protective equipment, including safety glasses, gloves, and footwear. Be aware of your surroundings and avoid contact with any exposed electrical conductors. Follow all applicable safety regulations and codes. If you are not qualified to work on electrical systems, seek the assistance of a licensed electrician. When selecting a location for a grounding electrode, consider soil conditions and moisture levels. Moist soil provides better conductivity than dry soil. Avoid locations where the soil is rocky or contains large amounts of debris. Choose a location that is easily accessible for inspection and maintenance. The NEC specifies requirements for the resistance to ground of grounding electrodes. Ideally, the resistance to ground should be 25 ohms or less. If the resistance to ground is greater than 25 ohms, an additional grounding electrode may be required. Ground resistance testers can be used to measure the resistance to ground of grounding electrodes. These testers typically use a 3-point fall of potential method to measure the resistance. The tester injects a current into the earth and measures the voltage drop between 2 points. The resistance is then calculated using Ohm's law. Regular inspection and testing of grounding systems are essential to ensure that they are functioning properly. Grounding connections should be checked for tightness and corrosion. Grounding conductors should be inspected for damage. Ground resistance should be measured periodically to verify that it is within acceptable limits. Any problems identified during inspection or testing should be corrected immediately. Proper maintenance of grounding systems can help to prevent electrical shock, equipment damage, and fire hazards. The integrity of the grounding system is paramount for electrical safety. Periodic inspections can reveal corrosion, loose connections, or physical damage to grounding conductors and electrodes. Corrective actions such as tightening connections, replacing corroded components, and repairing damaged conductors should be taken promptly. Ground resistance testing is crucial for verifying the effectiveness of the grounding system. Test results should be compared to the acceptable limits specified in the NEC. If the ground resistance exceeds the limit, additional grounding electrodes or other corrective measures may be necessary. Keep detailed records of all inspections, tests, and maintenance activities related to the grounding system. These records can be helpful for tracking the performance of the grounding system over time and for identifying potential problems early on. The NEC provides specific requirements for the grounding of different types of electrical systems and equipment. It is important to consult the NEC to ensure that your grounding system complies with all applicable requirements. This includes the type of grounding electrode, size of grounding conductors, and the methods of bonding. The NEC also provides guidance on the proper installation and maintenance of grounding systems. By following the NEC requirements, you can help to ensure that your electrical system is safe and reliable. Consider the specific needs of the equipment being grounded. Sensitive electronic equipment may require special grounding techniques to minimize electrical noise and interference. In these cases, isolated grounding systems or other noise reduction measures may be necessary. Educate personnel on the importance of grounding and the proper procedures for inspecting and maintaining grounding systems. Training should cover topics such as identifying potential grounding problems, using grounding test equipment, and performing basic maintenance tasks. Proper training can help to prevent accidents and ensure the long-term reliability of the grounding system. The electrical characteristics of different types of soil can vary significantly. Sandy soil tends to have higher resistance than clay soil. Soil moisture content can also affect its conductivity. It is important to consider soil conditions when selecting a location for grounding electrodes. Soil testing can be used to determine the resistivity of the soil. This information can be used to select the most effective grounding electrode location and to determine the number of grounding electrodes needed. A ground grid is a network of interconnected bare copper conductors buried in the earth. Ground grids are often used in large industrial facilities to provide a low-impedance grounding path for equipment and personnel. The design of a ground grid should be based on a detailed analysis of the facility's electrical system and soil conditions. The ground grid should be sized to safely carry the maximum fault current that could occur. A surge arrestor is a device that protects electrical equipment from voltage surges caused by lightning or switching transients. Surge arrestors are typically connected between the phase conductors and ground. When a voltage surge occurs, the surge arrestor provides a low impedance path to ground, diverting the surge current away from the protected equipment. Proper grounding is essential for the effective operation of surge arrestors. The grounding conductor should be short and direct, and the grounding connection should be clean and tight. The cost of installing and maintaining a grounding system can vary depending on the size and complexity of the system. However, the cost is typically small compared to the potential cost of electrical accidents, equipment damage, and lost productivity. Investing in a proper grounding system is a wise decision that can provide significant long-term benefits. The effectiveness of a grounding system is directly related to its impedance. Lower impedance means a more effective path for fault current. Factors that affect impedance include the length and size of grounding conductors, the quality of connections, and the soil resistivity. Careful attention to these factors can help to minimize impedance and improve the performance of the grounding system. Proper grounding is a fundamental aspect of electrical safety. By following the NEC requirements and best practices for grounding, you can help to protect people from electrical shock, prevent equipment damage, and reduce the risk of fire. A well-designed and maintained grounding system is an essential component of a safe and reliable electrical system.